I'm Mary Drosser, and on behalf of the College of Natural and Agricultural Sciences and the Department of Earth Sciences, I'd like to welcome you to our science lecture series this evening. As many of you know, we switched our speakers. Scott Dooney, who was meant to be speaking tonight, is in Washington, D.C., testifying to the U.S. Senate. You may know this is Climate Change Week at the White House, and there's a lot of hearings and things going on, and he was called in on Monday. But one of my colleagues has graciously accepted the invitation to speak, and we chose Gareth for a number of reasons. He works on earthquake processes, and we've gotten a lot of requests to hear about earthquakes and the type of research that people at UCR are doing. So we thought we would take care of that. And Gareth is, I was thinking as I was coming here, a rising star, but actually he's now past that, and a real leader, not that you're not young, but a real leader in sort of understanding the way that the Earth deforms, and he does this by using data that comes into satellites, sort of really interesting, really innovative ways of looking and analyzing earthquakes, and he is a real leader here. He came, leader in the world, he came to UCR in 2007, having gotten his bachelor's at Cambridge University in the UK, his PhD at Oxford University in the UK, and then did a postdoc at Berkeley. And very soon after arriving at UCR, Gareth got a NASA Early Career Award, which is an enormously prestigious and very difficult award to get. And tonight he's going to, I'm just looking at the picture, tonight he's going to talk about how he uses satellites and data from satellites to look at earthquakes here in California and elsewhere. Thank you.
Thank you, Mary. Okay. So, you've heard what my title is going to be. I'm going to talk a little bit about why I am qualified to talk about earthquakes, despite coming from a place that blatantly does not have any. And how I became interested in them in the first place. And it's really down to my mother, actually, I'm afraid. She took us on cool holidays in the summer to France, where I discovered these grassed-over volcanoes, which I got very excited about, and did when I was 9 years old, a primary school research project on earthquakes and volcanoes. I wanted to be a physics student at college until I started doing physics at college. And when the learning curve wasn't really a curve at all, but more like a cliff. And so I switched to geology because I'd always liked geology, and geology was great. I did PhD fieldwork in various exciting places, including Bolivia, where I tried to find evidence for earthquake surface rupture, and I also tried to find llamas. I found llamas, but I did not find the earthquake surface rupture, although it turns out with my radar techniques, I was able to find the earthquake, but I'm not going to talk about that today. And I actually moved to California because I studied earthquakes in the UK, and the UK does not have earthquakes. There's not really much of a future in the UK for someone who studies earthquakes. So I moved to California because there are earthquakes, and I'm going to bold that because many people don't take that view of earthquakes. But I came here because they are here. And I could go off and visit earthquakes in Mexico, the one that happened on Easter Sunday in 2010, and goof off in big chasms that we found in the ground. And also that lovely photograph of me sitting on the fault scarp. Anyway, so I am qualified, so this is what I'm going to talk about today. I'm going to talk about the basics of earthquake science, where and why and how earthquakes happen. And then I'm going to move into this technique that's called INSAR. It's a remote sensing technique that allows you to measure the movement of the surface of the ground from orbit. And so I'll show you how we use that to image earthquakes, and then how we also use it to image the loading of the ground, the loading of the faults that cause the earthquakes. And then I'll end with some idle speculation about what this might lead to in the future. There will be a lot of data, and maybe, well, I'll wait until I get there. Okay, so the basics first. The standard technique that we use, or traditionally have used to study earthquakes, is seismology. Assuming that you have a sensor that is able to detect the vibrations that are caused by earthquakes, these are called seismometers, then you can produce these things we call seismograms, and this is one here. And it shows essentially the strength of the movement of the ground as time passes, and you can see time scale is basically about half an hour covered by this record. And really what we learned early in the 20th century is that if you can identify the first two seismic waves to arrive, the P wave and the S wave, then the difference in time between the arrival of these two things increases essentially with distance from the earthquake. So if you can identify these two things and pick these two things, you can tell how far away the earthquake was from you when you make that measurement. And if you have a lot of these seismometers, then you can pinpoint the location of the earthquake. And this became a great opportunity for the military to help earth scientists, because at the same time that these sorts of ideas were these techniques were being sort of honed, there was a Cold War going on between the US and the USSR, and suddenly no one trusted each other when they said they weren't testing nuclear weapons, and so the one way to find out is to record everything that happens seismically on the Earth and then see if it's an earthquake or an explosion. I will point out also that the magnitude of an earthquake actually you get from how big these wiggles are, but I'm not going to talk about that today. So, within a few years of the installation of the worldwide seismographic network in the 1960s, we were able to make pictures that look a bit like this of where earthquakes happen on the Earth. And you can see that the earthquakes happen in very, very narrow areas, separated by large expanses of no earthquakes at all. And this was quite a fundamental discovery when it happened, and people gave names to the places where no earthquakes happened. They called them plates. And here are some of the names that are given to some of these plates, and there are several more on here that were too small for me to annotate. So yes, this led to a theory of plate tectonics, the idea that there were huge chunks of the Earth's surface that were rigid, that did not have earthquakes, that were moving as coherent chunks of rock along the Earth's surface. And we can measure those movements today using technology that you have in your cell phone, but also in rather more impressive looking pieces of equipment like this. This is the GPS station, somewhere in Alaska, I think this one. And essentially it tracks signals from satellites and allows it to pinpoint its position to better than a few millimeters every day. And as the ground moves and the GPS station moves, we're able to track that movement. So that's really cool. And we can see, for example, that the Pacific plate, which is this one, with these red arrows, is moving in a completely different direction to the North American plate, which is this one here. In fact, you could blame, perhaps, Japan or Alaska or maybe Kamchatka, Russia, for all the earthquakes we get in California, because what's going on as this plate is moving towards there, it's being dragged down into the mantle by a process we call subduction. And so that's pulling the whole of the Pacific plate northwestwards towards Japan and Alaska. And it's dragging, essentially, on the boundary of the two plates here, and causing us a lot of grief and a lot of earthquakes. Just to point out where you are, you're right where the action is taking place. So at this point, I'm going to launch into my one slide public safety announcement that you really need to have earthquake supplies in your house, because it's not really a case of whether you'll have an earthquake here in your lifetime, but when. And we still cannot predict earthquakes, but we can definitely prepare for them. So what do you need in your earthquake emergency kit? You need at least a gallon of water for every person in your household for at least 3 days. And you need food that does not perish, and you need to keep that with a first aid kit, fire extinguishers, flashlights, radios, batteries, and anything else that you might neglect. Hopefully not. Your medications, your diapers, baby formula, dog food, all the works. Put it in a big rugged plastic container, put it somewhere where you can get to it in case of a disaster. And then also we advise that you make sure that your house isn't going to kill you. The most common cause of injury in earthquakes these days are the contents of the house, not the houses themselves. So bolt your furniture to the walls, and make sure that you don't have giant mirrors above your bed that can fall on you and slash you in your sleep. Make a plan of who to meet and where to meet, who to talk to out of state or out of region anyway, so that if something bad happens, that you have a third party that other people can contact and find out that you're okay, and know what to do in the case of an earthquake. And it's not run outside. It's protect yourself from flying objects, which you can typically do by climbing under a sturdy table or chair or something along the lines of that, and holding on to it for dear life until the shaking stops. Okay. Follow these web links to find good sources of information on all of that. Okay, back to California. So I hopefully made the case that the Pacific Plate is dragging on California at about 50 millimeters a year, which is about 2 inches a year of movement. And that movement is taken up on a bunch of faults in California. And here are some of the most famous ones. This orange guy that runs from Cape Mendocino down to the Salton Sea is definitely the most famous fault in the world, the San Andreas. But given our location in Riverside here, you may also want to know and worry about the San Jacinto Fault, which runs through Moreno Valley and Redlands, and certainly should not be neglected. The ones I've highlighted are actually the ones that are considered most likely to have a major earthquake in the next 30 years. And as you can see with the southern San Andreas Fault, the section of it that runs here from Mount San Gorgonio to the Salton Sea, is considered the most likely part of the most likely fault in California. It's probably more likely than not that it will experience an earthquake in the next 30 years. So you want to be aware of that. But what is a fault? Now here they're drawn as lines on a map, but geologists think of them more as surfaces within the Earth. Surfaces where essentially the rocks are weak and the rocks will break. So you could have 2 blocks of rock on a map separated by a fault, and what we would imagine as geologists would be two volumes of rock separated by a surface. And these 2 blocks of rock could be, for the sake of argument, the Pacific Plate and the North American Plate in our case. So most of the time, faults don't move. They're locked by friction. The friction of this rock surface rubbing against this rock surface means that the fault doesn't move. But as I showed you, the Pacific Plate is dragging on California the whole time. And so what's happening, and slowly over time, is that these blocks of rock are becoming warped. They're becoming bent by the tectonic forces, this drag of the Pacific Plate on North America. At this point, I brought with me a yardstick to do a demonstration of elastic strain, mostly because I like twanging rulers. But essentially what's happening over time is that we're bending the crust, and when that energy is released, you get a release of sound energy and vibrations. And that's kind of what an earthquake is like, of course, though they tend to be a little larger and a little bit more devastating. And that's because you're bending granite, not bending wood. Granite is a lot more rigid than wood. It takes a lot more stress and a lot more energy to bend it at all. And I was only bending that maybe 5 centimeters. And in the crust, you could bend it several meters over a volume of rock that's maybe 100, 150, 200 kilometers long and 15 kilometers deep. That builds up a lot of energy, and when that's released, you'll know about it. And the way that it actually is released, the fault is locked, as I said, by friction. If I put my hand on the end here and lift it, this ruler is being kept in place by the friction between my hand and the wood here. And as I keep pushing it up, essentially, the stress that's pulling on my hand is getting greater and greater and greater, and eventually it's going to give. The pulling stress of the bent wood is stronger than the friction that's holding it on my hand, and that essentially overcoming of the frictional strength of a fault is what causes an earthquake. Although I can say they're a bit more devastating than that. Sorry about that. So this loading process can take hundreds of years, and it goes something like this. We get more and more bending, and then one day, when the bending stress is bigger than the frictional strength of the fault, you get all sorts of craziness going on. These are all pictures from the Northridge Earthquake in Los Angeles in 1994. At the end of all of a single sort of cycle of loading and then unloading, the earthquake being the unloading, what you end up with is the crust returns to its original dimensions, but it's offset by some distance along the fault. We call this elastic rebound. So you build up elastic forces and then you release them, and then everything rebounds to their original shape. So to summarize, we call this the earthquake cycle, or the elastic rebound process. You have maybe 200 years of slow loading, slow bending of the crust, and then about 20 seconds is all it takes to unbend it back to its original shape, and of course not without a lot of shaking and damage, probably. One thing I would like to stress is that the seismologists among us are very good at studying this part of the process, the 20 seconds of rapid unloading the earthquakes. But the techniques that I use allow you to measure both the loading and the unloading, and so that's why I think it's cool. All right, so moving on. Part 2, studying earthquakes from space, or imaging them. This is an artist's impression of one of my favourite satellites, ERS-1, launched by the European Space Agency in the early 1990s, and yeah, legendary. But anyway, we'll get there. The technique I use is called INSAR. I don't really think you need to know what all those things mean or stand for, but for completeness, people always ask. It stands for Interferometric Synthetic Aperture Radar. Interferometric talks about wave interference. If you know what that is, great. If you don't, it doesn't really matter. Synthetic aperture, that means that you pretend that you have a really big radar antenna in space. You can't launch a really big radar antenna into space because the rocket costs would be astronomical. So you just pretend that you have a really big antenna by moving it, and it moves because it's on a satellite, so that's okay. And then radar. Well, radar is a technique that's been around since the Second World War, and it involves beaming radio waves at something, or microwaves, and measuring the returned echoes. And certainly we do that. But in this case, the radar antenna does not rotate like they do at airports here. It's fixed to the satellite, and it's pointing in only one direction. So what we have essentially is a satellite, this guy here, ERS-1, and it emits a radar pulse, and the ground will either reflect it away into the ether, or some of it might be backscattered back towards the satellite, and we'll record it back at the satellite. That means that if the ground is very smooth, you don't get much radar coming back to the satellite. If the ground is very rough, you get lots. And we record both the amplitude of the reflected radiation and also the phase of it back at the satellite. And a little primer on amplitude and phase. Amplitude is just how strong your waves are. So amplitude is essentially how big your peaks are if this was a radar wave. And then phase is really where you are within one of these cycles. So it's like the distance along this line between, say, here and here, or something like that, would be a difference in phase. And that's important, I'll tell you in a minute, for this technique. Amplitude images from SAR satellites are really pretty, or they can be. They're used to image areas that are difficult to image any other way. Because you're beaming your own radiation to the ground, you don't need it to be daytime. That's really useful. You also don't need it to be sunny. It could be cloudy, and this will still work. The radar will see through the clouds and see what's on the ground. So the Europeans were very big on these satellites, and so are the Japanese, because they have bad weather, basically, and it's very helpful. This is actually the Kilauea caldera on Hawaii, and Halemaumau crater, where there's sometimes a lava lake. And you can see that the ground has differences in roughness. Some places are brighter than others. Those are rougher pieces of ground. So some places it's smooth, some places it's rough. And you see some places where there's different, there's bright spots and dark spots. And that shows you that the radar was shining towards this side of the caldera. And that slope is pointing towards the satellite, and that's why you get a bright reflection. More radar is returned from there. So this is used for all kinds of things that you want to track things day and night, such as icebergs, ships, oil slicks, all that kind of thing. It's also used to image planets. Quite often, the Magellan mission to Venus, which is famously surrounded in clouds and impossible to see from with optical imagery was very successful for studying Venus. Anyway, I'm not going to show you any more of these pictures. I'm going to talk about the phase. And really, this is the key to the whole thing. Phase is related to how far away the satellite is from the ground. And so, in normal circumstances, if a satellite comes back a few months or a few weeks after the first time it passed over something and beams the ground, you should get the same phase. You should see the same distance between the satellite and the ground. But if the ground moves, then you will have an additional amount of phase, an additional phase shift. And we can record that back at the satellite. So if you subtract the phase of one image from the phase of the other, you can detect how far the ground moved. And that sounds like wizardry or something, but it works. And I'll show you in a minute. And not only that, but what we have learned is that for various things, like this being an earthquake, a little normal faulting earthquake, this side being pulled down essentially by the fault, that the amount of phase shift that you get depends on where you are with respect to the fault. If you're a long way away, you see very little phase shift. If you're quite close to the fault, you see quite a big phase shift. And we can use those kinds of observations to understand the earthquake that happened or the other process. This also works for anything that moves the Earth's surface. So some examples. All right, so here are amplitude and phase images from two different dates in 1999 in August. This is an area of Turkey, and the city of Izmit is here. This is the Black Sea. This is the amplitude, and it looks a bit like a satellite photograph. And this is the phase, which looks like nothing at all. And this is an image taken 35 days later by the same satellite. Again, amplitude and phase. And the only thing we use the amplitude images for is to make sure that we completely correctly overlay one image on the other. Make sure that they match up perfectly, and then we throw that information away. And what we do then is take the difference between this and this. And somewhat unbelievably, what you get out of it is this. And this is what we call an interferogram, and it is essentially a picture of how the ground moved in that earthquake. Okay, I'll let that sink in for a second. Right, so how do you interpret that, what I'm showing you there? Well, really they're like contours of how the ground moved. So if you've ever been used to reading a contour map, you know when contours are close together, there's a rapid change in height on a topographic map. Here it's a rapid change in displacement of the ground. The ground moved more over the same distance, essentially. So if we pick an area to be one of these lines to be 0, then one color cycle, in this case, represents 28 millimeters of movement of the ground towards the satellite. The satellite is in orbit, looking in this direction. This arrow saying LOS means line of sight. So that's the way that the satellite is looking. So this piece of ground essentially moved to the west. You can count the next one, 28 millimeters, 57 millimeters, and 10 fringes in, we call these fringes, 28 centimeters of movement towards the satellite, and then 57 centimeters of movement towards the satellite, and you can see that these get closer and closer together until you get to essentially this line here, which is where the actual fault was that caused the earthquake. So what we're measuring over time, over distance, is essentially that the ground moved more and more and more as you get closer and closer and closer to the satellite, to the fault. Sorry, and see the reverse trend on the other side of the fault. Essentially, it's moving further and further and further that way. If you think back to the pictures of the ground unbending, this is the kind of unbending that you would need to have in order for your blocks to regain their original shape. If you recall, in the period of bending, the areas far away from the fault were moving a long distance, and the areas at the fault weren't moving at all. Now, in the earthquake, the ground near the fault moves a long way, and the ground far away from the fault doesn't. So when you add those two together, you end up with what you started, which was undeformed crust, or at least that's the idea. So we can learn a lot about earthquakes from this. Essentially, the amount of displacement near the fault is related to how big the earthquake was. So larger earthquakes will have more movement. hopefully makes sense. Yeah, there are various different styles of earthquake, and we can tell which of those an earthquake was from the pattern. Here's another type of earthquake. We call this a normal fault. In this case, what the earthquake has caused, and what the satellite has imaged, is a depression that formed in the Earth's surface. 10 kilometers is about 6 miles, so this is about 6 miles wide and about 5 miles across, something like that, and 10 centimeters deep, which is about 4 inches. And you would not be able to tell that this had happened, I don't think, if you went there on the ground. But if, for example, it rained very steadily for a day or so, you should get a puddle forming that would be about 10 kilometers wide by 8 and about 10 centimeters deep in the middle. So that's the kind of scale of the thing that you're measuring. You would never be able to tell this, I don't think, from making field observations. So this is where satellites win over geologists. And then we can do things that we can come up with theoretical models. So this is an earthquake that happened in eastern California, somewhere near Lake Tahoe in 1993. And you can see that we made a model of this earthquake, and this was the original data, and they look pretty similar. And when you subtract this from this, you get basically noise, which is good, which means we explain the earthquake. And for the geologically inclined among you, that means we can find out things like the strike of the fault, the dip of the fault, the rake of the fault. In other words, what its orientation was in space, and what angle it was inclined at, and how far it moved, and in what direction. And we can tell its magnitude and all sorts of other things. So this has kept me and my students busy for a while. This one was produced by my student Jenny Weston, and this has been a major thread of my research since I was a graduate student, and I'll show you some more examples in a second. Just to point out that you don't just have to study earthquakes with this. You can study all kinds of other things. So on this image here, this is of the margin of South America, starting in Peru and moving all the way down through Chile. What you can see is that there were 4 large earthquakes on the coast, and that's what these 4 things were. This is a slide made by Matt Pritchard, who's at Cornell University. I really like it just because you see these 4 enormous clusters of fringes. There are hundreds of kilometers across. And then located next, enlarged all around here, this one here is this. This one here is from there, and there's a couple more down here. These little pimple things are actually volcanoes. And what these are showing essentially is a rising of the edifice of a volcano upwards or down or contraction of it downwards. So in this case, we can see magma coming into a volcano. That might mean it's more likely to erupt. That might be important things to know. And you can also see the opposite. If the volcano starts to subside, then that means the magma has gone somewhere else, and it's not going to be necessarily a threat to erupt. So we can use it for those kinds of things too, which is great. And we can study places that you'd never be able to go and study on foot. In the high Andes. Okay, over here, what this is showing you is the San Francisco Bay Area. This is actually the city of San Jose. And what you're seeing is essentially the difference in elevation between the elevation of the ground in 1992 versus the elevation of the ground in 1998. And in that time, the ground has risen 30 millimeters. And not because of faulting or anything else, but because of increased water storage in the ground. There's an aquifer, which is used for groundwater, for drinking water, under this area, and they slowed down the amount of water they pumped out of the ground. So over the course of a decade, the ground swelled up like a sponge, about 30 millimeters. And you can see that, which is amazing. And then here is a glacier. And essentially, you can see the middle of the glacier is moving quite fast, and then the edges of the glacier are moving like crazy. So most of the strain in a glacier is taken up essentially on the edges, and the middle of the glacier doesn't deform nearly as fast. Measuring glaciers is kind of difficult because they move too fast, but here is one that they successfully managed to measure in Alaska. Okay, but I'm an earthquake kind of guy, so I'm going to look at some earthquakes with you. This is one that is very dear to my heart because it was really the subject of my first publications. This earthquake that happened in Iran in 2003 in the city of Bam. It was a disaster by any proper measure. It killed anywhere between 20,000 and 40,000 people, depending on who you believe. The official death toll was, in the minds of some, artificially low because the Iranian government didn't want to look bad. The main problem was that, as you can see, all the buildings in this town were made of adobe, essentially made of mud, and does not have does not behave well when it's shaken strongly. And it surely was shaken strongly. They measured ground accelerations of approximately 1G. In other words, the same force that's holding you to the ground was temporarily reversed and then doubled on the ground in the shaking. So things went from being weightless to being twice as heavy, and no building can withstand that, let alone mud buildings. So it was really bad. And then when the dust settled and we figured out where the earthquake initiated, it was only 10 miles away from the city. So they really were in the middle of it before it. And they didn't have any time to respond at all. It was too quick. So that's bad. This area had been identified as one that might potentially face a seismic hazard because there's this thing that you can see in satellite images, this fault here that has a topographic ridge associated with it, and geologists were pretty certain that's where the fault was going to break and where the earthquake had been. And so when field geologists went to the area, they went there. And found very disappointing evidence of almost nothing. So you can see there's a crack along the ground, but for an earthquake that killed 30,000 people, that's pretty slim pickings. So they were very confused. But they should have waited to talk to us in Oxford, who basically was sitting on this image within about a week of the earthquake happening. And what you can see here, perhaps, is the signal from the earthquake, which is complicated, and I'm not going to get into exactly what it all means, but you can see that there is a signal from an earthquake here. And you can also see that there's a whole blank spot where essentially there used to be two towns. This was Bam, and this was a place called Baravat. And we lose signal here because essentially the ground changed completely. Where there were buildings, there is now rubble, and the radar can't correlate those two. So actually, you can also measure damage with INSAR, and that was a lot of damage. But some of the damage is kind of interesting. This feature down here, sort of suspiciously long and straight, that leads straight out of the city of Bam, turned out to be the surface rupture of the earthquake. So we told them to go there. They went there, and they found it. So again, this is where a person sitting at a desk can do better than a field geologist. Not that I like to criticize field geologists because they do things that I really cannot. So when you look at where this fault was compared to the mapped fault, it was actually 4 kilometers to the west, and we had no idea it was there. So even with all of our current abilities to identify faults from satellite images, this fault would have gone completely undetected, and that's kind of a problem. So that's something that we're working on, ways of figuring out how to find these faults that don't show themselves in satellite images. But anyway, the earthquake itself has really pretty data. We have data from the satellite when it's flying from south to north. We call this ascending mode, and also when from north to south. The pattern's completely reversed, as you can see, or almost completely. That tells us that the motion in the earthquake was horizontal. But the details of this are actually quite complicated, so I won't go into that. But I will point out that you can identify the same feature on the same side of the earth of the fault in both images. This teardrop-shaped thing, and that actually requires there to be two faults that moved in the earthquake. One that went through here, and another one that went through there. Something like that. And this is our attempt to model it, and this is what happens when you subtract that model from the data. So it fits okay. The details in the near field are always difficult to fit, and it's just a function of how really amazing the data were in the first place that we had this trouble of not being able to fit every single bump and wiggle. I don't think anyone has managed to fit every wiggle on this. So when you plot where the second fault was, it actually was maybe related to the mapped fault, but it did not break the surface, and so that's why people had trouble explaining it. One other feature of this earthquake, just to conclude, was that these two faults, we think, intersected at depth. at about a depth of about 8 to 10 kilometers, somewhere around there. When people went out and measured the aftershocks of this earthquake, they started at about that depth and they extended down for another 10 kilometers below that. So we think from this that all that's happened is the shallow part of the fault has had its earthquake. And there's still a chance the deep part of the fault could still have an earthquake in future. And presumably that would not be a good thing for the city of Bam, which is currently being rebuilt. Great shame, if that's true. All right, and then we're going to look at somewhere a bit closer to home. Another earthquake. I had a graduate student of mine worked on this. The 1994 Northridge earthquake. And did any of you in the audience feel that earthquake? Yeah, I thought you might have. It was quite a big deal, I think, for the people who were around at the time. This is my favorite picture of an earthquake ever, I think, because it manages to combine a flood and a fire at the same time. This is a great picture of the 5 freeway with these poor guys in the big rig sort of stranded on a trestle of freeway. I think everyone was evacuated from there without any injuries. And it did a number on a number of parking structures and buildings in the greater Los Angeles area. So the data we have from this earthquake are a little more slightly different. We have a circular pattern here, and when you actually look into the details of it, it's about 60 centimeters of uplift centered on the city of Northridge. That's about 2 feet of uplift. And this is consistent with this being a thrust fault. In other words, one chunk of rock is being pushed up on top of another chunk of rock. We call that a thrust fault. There are quite a lot of them in Los Angeles. We took the opportunity to use the efforts of the Southern California Earthquake Center to make a model of every fault in the Los Angeles area. This is quite a complicated mixture of surfaces, as you can see, and most of them are thrust faults in the greater LA area. But the one that we're interested in is this little guy in here, the Northridge Fault. I've attempted to plot it in a way that you can see that its shape, but essentially it's kind of hard to see. But take it from me that essentially there are 2 flat parts of the fault and then a ramp in between them. So it's got a kind of a sort of step in it, but it's tilted. So I don't know. If anyone can mime it better than me, please show me afterwards. But when we actually solve for how much each part of that fault moved in the earthquake, we get a pattern that looks a bit like this. It moved about 2.5 meters on this patch here, and about 2 meters in general are in this area around here. And I'll talk a little bit more about that. And it went down to about 15 kilometers depth, 10 miles, or 9 miles. My model is very successful at fitting the data. Here's the interferogram, here's the model, and that's what you get left over when you subtract it out. 2 different interferograms. It fits quite well. But yeah, the observation that the fault moved furthest here is kind of interesting, because that's actually on the corner of the ramp on the fault. That's the bit that's probably jutting out the most, the point perhaps where the fault is under the most stress, because it's the part that's gouging into the overriding chunk of rock. So perhaps if we could look for plenty more cases of this, where there's geometrical sort of ramps in the fault, and maybe those will be the places that experience the strongest movement and maybe the strongest shaking. So it's possible that this is useful knowledge for other places in LA. So people have been at this for about 20 years now, this idea you can model earthquakes using this INSAR data. And 101 earthquakes have been studied this way. That's where they all are. They're all in places near plate boundaries. But one thing that we have noticed, we being my students and I, is that the locations that we get from INSAR sometimes differ quite strongly from the locations that the seismologists were able to find. Here is one example of that. This arrow here is 10 kilometers of difference in location. The arrows are drawn from where INSAR says the earthquake was to where seismology says the earthquake was. And some places, earthquakes are mislocated by 50 kilometers, 30 miles, which you think would be noticeable. So it seems to me that we could possibly help out the seismologists here by telling them where their earthquakes happened, and then they can improve the models of the Earth's velocity, seismic velocity that they use to locate earthquakes, and maybe start locating earthquakes in the right place. Okay, so that's my spiel on earthquakes. But of course, as I tried to show you earlier, earthquakes are only half the story in the earthquake cycle, and only really the shortest part of the earthquake cycle. The other part of the earthquake cycle is the 200 years of bending of the crust that takes to build up the energy to have the earthquake in the first place. And it turns out we can measure that. Okay, so what do you want to know, really, if you're interested in seismic hazard in this area? Well, you want to know two things. You want to know how fast the crust is bending, and you want to know when the last earthquake was. And if you know those two things, you have a fighting chance of guessing how big the earthquake could be when it happens. You still can't say that you're going to know when it's going to happen, unfortunately, because they don't seem to give any signs of speeding up or slowing down in the bending before an earthquake. But we will hope maybe to have the capability of seeing that one day, perhaps. So yes, we want to know these two things. And I'll first work on the part about how fast the crust is bending. So this is tricky to measure with INSAR because INSAR is affected by noise. And the signal that we'd be looking for would be essentially 2 centimeters, which is less than one of those fringes, every year, probably, something like that. So that's tricky to see in a single interferogram when you get things like this happen. This is an interferogram of Los Angeles. Los Angeles is over here. This is Palos Verdes. We're somewhere in this corner. And what we're seeing here is essentially noise from the atmosphere. This was a day when there was turbulent air, and it caused the radar signal to be refracted in a way that looks like all these little swirly blobs. So if there was a very subtle signal in here, we wouldn't see it. So this means we have to use a lot of data and a lot of effort to get at these more subtle signals in INSAR data. And this is just saying, again, atmospheric noise can mask, perhaps, the small signal from bending the crust. So one solution is to cherry pick the best interferograms you can find and add lots of them together. And that way, any noise that's in the data, which should be random, will be overpowered by the signal, which should be correlated and should be the same in all the interferograms. So if you stack, as we say, multiple interferograms of the same thing, the sum of these 4 interferograms turns out to be something that looks like this, where you have essentially a red area that's moving towards the satellite at a certain speed, and a blue area that's moving away from the satellite at a certain speed, and the transition between these two is essentially the bending of the crust, and it's occurring in this zone here. This is an example from Turkey. We can do this in lots of places. Where I actually apply this kind of method is to Northern California. So this is San Francisco Bay Area here. San Francisco's there. And I can see all kinds of things in this that I wasn't looking for, it turns out. When you make an image like this, you actually image every single thing that's moving the Earth's surface, not just the faults. So I'll show you what those are. This is a geothermal field in Northern California, which is the largest in the world. It's just over the hill from Healdsburg. So if you drive for about half an hour up really windy roads from the city of Healdsburg, from the 101, you end up in this place where there are 20 power stations in about 20 square miles. And it's incredible. I do field work there, but unfortunately not enough time to talk about all the things I see today. All these features here are groundwater of one sort or another. Some are going up, like these blue ones. Some are going down, like these red ones. So that was the one I showed you earlier in San Jose, and then there's some other groundwater basins elsewhere in the Bay Area. And then a whole lot of red around the edges of San Francisco Bay and San Pablo Bay. This is all subsidence. These are all buildings that are sinking slowly into the ground, mostly because they're built on landfill or on mud on the edge of the coast, which is slowly settling and compacting and taking your waterfront property probably to water level or below. Okay, so that's great, but you can also see you can see tectonics too. You can see a transition from red in the far west to blue in the east, and that is essentially the action of the Pacific plate moving away from you over here and moving towards you, and North America moving towards you over here. So this shear is the plate motion. And in most places, like in San Francisco, you see no sharp jump in velocity at the fault. The fault is not moving, it's locked. But strangely, in the Bay Area, there are a number of faults that aren't locked. They seem to be moving. So here, on the Hayward Fault, if you take a profile through here and look at the velocity, it suddenly jumps up when you get to the Hayward Fault. So this side is moving at a different speed from this side. It's almost like one side is moving away from you and one side is moving towards you, right at the fault. This is an unusual phenomenon called fault creep, which is seen in a few places in California, and this is why I was working on it. And the Hayward Fault is one of the best places to see it. It's absolutely, these data are lovely. It's good for people who live in and around that area, because where a fault is creeping, it's not locked, and where it's not locked, it's not storing elastic strain. So you're not going to have such a big earthquake there, because it's releasing the energy that should be powering earthquakes straight away. It's not to say that there won't be another earthquake there, because our data shows that at depth this fault is locked somewhat. And so, the earthquake would be a lot larger if the whole of the fault was locked than just a portion of it. But that's Northern California, and people don't like to hear about Northern California around here. They like Southern California. So here is the same kind of data, but from the Salton Sea area. So this crosses the San Andreas Fault and the San Jacinto Fault. San Andreas Fault is here, and the San Jacinto Fault is here. This is not my data, unfortunately. I'm working on an area further north I'm not quite ready yet. But this gives you the general idea. You have a transition from blue over here, which is moving with the Pacific plate, to red, which is moving with the North American plate, and in between you have the zone of bending where the strain is being sort of accumulating on these two faults, the San Jacinto and the San Andreas. And what that looks like, if you take a profile through it, are some of these kind of gentle bending curves, and two of them. One for the San Andreas here, and another one for the San Jacinto. And you can see that in this area, they're almost the same. They almost have the same vertical extent or vertical size. This would be the amount of slip or the amount of strain that's accumulating is about the same. It's a bit more for the San Andreas than for the San Jacinto. But you can fit a model to this and then figure out how fast the crust is bending, and therefore how quickly it's reloading for the next earthquake. And those data suggest that the San Andreas is reloading at about 25 millimeters a year, or 1 inch per year, and the San Jacinto Fault at about 3/4 of an inch per year, 19 millimeters per year, in this particular area. So knowing that, and then you probably want to figure out then when the most recent events on those faults were, so you can say, well, how much time have we had to build up elastic strain for the next earthquake? On the San Jacinto Fault, very close to us, there were two earthquakes essentially in the early 20th century, more or less 100 years ago. A magnitude 6.8 in Hemet and San Jacinto, and then another one, a 6.3 in Moreno Valley and Redlands in 1923. That's pretty bad. That's quite a long time since those earthquakes, but not as bad as the San Andreas, which has not, in the Coachella Valley area, had an earthquake since people were writing history in California. So the first missionaries who took written records arrived in the late 1760s, and they haven't felt any earthquakes from that area, and they're pretty. They were pretty active in writing about every weird phenomenon that they experienced everywhere else in California. They provide a really good written historical record of all the earthquakes that have happened. So the fact that they didn't write about any suggests that there weren't any. And then geologists have actually gone and dug holes through the San Andreas Fault in various locations through here and looked for the oldest sediments that have not been disturbed by earthquakes. And you can carbon date those, and you get an age of about 1680 for the last earthquake occurring on that fault, which is 330 years ago. They also find that the mean recurrence time, the last 5 earthquakes on that fault, I think, were 250 years apart. So this is already 80 years overdue. So think about that earthquake hit. How bad could it be? Well, if you do the sums, 100 years at 19 millimeters per year is 1.9 meters of potential fault movement in the next earthquake on the northern San Jacinto Fault. That gives you an earthquake that would be in the range of a 6.7 to a 7, although there's quite a lot of uncertainty in those numbers, so I wouldn't take them as gospel, but you should take it as motivation to be slightly worried. The southern San Andreas, 330 years plus 20 times 25 millimeters per year is 8 meters of unreleased stored elastic strain, and that could be a magnitude 7.5 to 7.6 earthquake, so that gets a double exclamation point. So bear that in mind. Okay, so that takes me to the last part, which is the future. And you may not have been aware of INSAR in the past, but I suspect that increasingly this will be a very commonly used data site. And the reason is because the European Space Agency are launching, have already launched one, and and are planning to launch another satellite. And these will be flying in a constellation in the same orbit, such that every 6 days one of these satellites will pass over every point on the Earth's surface and take an image, which means that the amount of data that we're going to get is going to be about 10 times more than we've ever had. So we're going to have the opportunity to image things in a very, very short time after earthquakes, and also to do ongoing monitoring of processes, movements on the ground. So you can think perhaps the volcanoes, you can measure see if they're swelling up dangerously over a period of time, or whether, if this does happen, and we still don't know, whether a fault starts to accelerate in its bending. That would also probably be a cause of some worry, but we might know in advance, and that would be the idea. The Japanese are also launching a satellite in about 2 weeks. Theirs is actually designed to work better in vegetated areas, which is good for my work in Northern California. It has a different radar wavelength, and that helps you see through the trees and things. And sadly, NASA have been trying to launch one of these satellites for a very long time, but they never make it through review. So there's a group at JPL who spend years and years of their lives putting together mission proposals that somehow disappear when they get to Washington. But this one, the most current of their proposals, NISAR, stands a good chance of getting funded because it's a joint operation with India, and the Indians are very keen, and they're quite dynamic in comparison, so they're pushing for it. So it might happen. It passed a certain critical review about 2-3 weeks ago, which makes more of us optimistic. So maybe there will be 3 constellations of satellites out there that will help us monitor the Earth. So what can we expect? Well, we'll get regular routine analysis of earthquakes. Everyone's working towards automating this, so I'm sure that will happen soon. Using the degradation of the signal from damage that I showed you in the city of Bam, people have actually started to apply that to damage mapping from typhoons, from other earthquakes, from tsunamis. So even if there's no movement of the ground, you can detect whether the ground has been damaged. And I think that will be a major application of this in the future. And then some of my more fanciful colleagues suggest that what we might come to expect in future are sort of tectonic forecasts, a bit like you get weather forecasts and you have satellites measuring clouds and where they're moving. Well, you might be able to also measure the bending of the crust and whether that's increasing, and that means certain areas are more risk of earthquakes at a given time, or something like that. Who knows? We'll see. The future is approaching, I guess, fast. So in summary of all the things I've said, I want you to take home that earthquakes are actually the sudden unbending of the crust, which follows decades of really slow and difficult to measure bending. But INSAR, unlike seismology, allows you to measure both of those things. So you can measure the bending and the unbending, and you can get the full picture of the earthquake and the process that caused it. We also get, every time we look at an earthquake, we seem to find something new. In the case of the BAM earthquake, we found a whole new fault that we didn't know was there. And we also found that there might be a possibility of a future earthquake just from looking at where those faults were and where the aftershocks were. And of course, we can more accurately locate those earthquakes than seismologists can, which is also good. And we will be able to use this to measure fault loading everywhere in the world, and we can also measure a lot more than just fault loading: volcanoes, landslides, glaciers, everything. So thank you.
So everybody's going to go home and do their earthquake kit, right? But before then, we will take a few questions. If you guys have questions, raise your hand. I think we have somebody with a mic. Do we? 2 mics? Yeah, so go ahead and raise your hand. There's a gentleman here.
He's behind you.
Yeah, he's got it.
Hello. Recently, Long Beach, I don't know if were selected for a pre-earthquake, some type of monitoring. Have you heard anything about that? It was announced maybe just a few weeks ago.
I'm afraid I don't know. I know that they have installed a lot of seismometers in Long Beach because of they're monitoring all the oil extraction that's going on there. And I've seen some really, really cool data from that, but I'm not sure about.
What do we know about segmentation of the southern San Andreas Fault, and what does that mean in terms of potential magnitude?
So that's a question asking about how connected is the San Andreas to other parts of the San Andreas Fault. The southern section of the San Andreas Fault is runs in a pretty straight line from the Salton Sea to the San Gorgonio Pass region, and then it takes a horrific bend through the mountains, and that would be what we would call the part from the Salton Sea to the mountains would be one segment, and then the part that goes through the mountains would be another. And I don't think that, well, there's a lot of debate about whether an earthquake could actually make it through that bend or not. And this earthquake could be this big without it having to go through that bend. If it made it through the bend, it would be worse.
So I guess, do people think that the entire southern San Andreas Fault is going to rupture at once?
People are very divided on that.
Is there a relationship between earthquakes and volcanoes?
Some people have claimed that after the Sumatra earthquake, the volcanoes in Sumatra were more active. I don't know of what exactly the mechanism for that would be. Maybe the shaking could loosen the bubbles in the magma chambers and actually flush more magma out. People have speculated about it. You also see a lot of small earthquakes in volcanic areas following large earthquakes nearby, which might be part of the same process.
There's somebody, gentleman in the back, way back.
Yes, you said that we are about 80 years overdue.
Yeah.
With your expertise and your knowledge, can you give us a narrow when this one will happen so I can better prepare?
Unfortunately, no. I'm afraid not. 80 years ago, maybe?
Is there anything related between drilling and causing earthquakes, or any man-made drilling that is exacerbating dens at all?
Well, yes and no. It depends on...
In your opinion.
It's not just my opinion. So fracking, which is thought to be like the cause of all kinds of badness, is actually not a major cause of earthquakes, because the amount of rock that they're actually fracturing is usually very thin. However, conventional oil and gas production, one of the means that they use to flush out more oil or gas from the reservoir is to pump more water down into the well, so as to flush out the oil and the gas. And that is not confined to such a narrow layer and actually can cause big earthquakes. And many of the earthquakes that have been occurring in the Midwest and in the South and the Southwest have been tentatively linked to that.
Okay, well, great. Thank you very, very much.